like to welcome you all to the CIBM Center for Biomedical Imaging Breakfast and Science Seminar Series. We're at number 19 now, the penultimate of the year. And it is my great pleasure to introduce to you Micah Murray, who is the head of the CIBM EEG Shiver section, who will be chairing the session. And of course, our speaker for today was Pascale Sandmann. And thank you, Micah, for hosting the event and for introducing Pascale.
My pleasure. So if I could just share my screen, we are indeed very privileged to have Pascale Sandmann with us today. Her research foci focus on audiology, hearing loss, and plasticity, which are extremely important societal issues, as well as very pertinent domains of basic research. She's been recently habilitated in the field of audiology at the University of Cologne, where her current position is. But before that, she is and remains a very proud Swiss, trained here in Zurich, back at the ETH Zurich and University of Zurich. She's procured more than 600,000 in external third-party fundings, and she's very well published, as well as very well cited. But most importantly, I think it's important to situate a little bit her work in the domain of cochlear implants and its effect on hearing loss and brain plasticity. Pascale's work is really at the cutting edge of this and has been for many years, which is part of the privilege that I have, in particular, of interacting with her and collaborating with her. She has been looking at this very old neuroprosthetic device, the changes it makes in the brain, and this is a particularly interesting case where EEG is actually the best suited technology to be looking at such individuals. Because of the technology itself, it's difficult to use other imaging modalities to investigate such patients. Just as a little historical trivia, the first implant in Switzerland was actually back in 1977 in Zurich by Professor Fisch. And in Switzerland, they're performing about 150 of these implants per year. So this is a very pertinent domain, not only for Swiss research, but also globally. And we're very privileged today to have Pascale tell us a little bit more about some of her ongoing activities. So thank you very much, Pascale, for joining us. We look forward to hearing your lecture this morning.
Thank you very much, dear Micah and dear guests, for introducing me so kindly. And I'm very honored to speak today. And I would like to share my screen. Good. The title of my talk is Seeing While Hearing, Altered Audiovisual Interactions in Patients with Cochlear Implants. So everyday situations are multisensory. When we communicate with each other, we use the auditory system, the visual system, and these systems, of course, interact with each other. And this lecture is dedicated to the question how audition and vision interact, not only in normal hearing listeners, but also in patients who have sensory neural hearing loss and who are supplied with a cochlear implant. So this is the overview of my talk. I will first give you a short introduction about cortical changes after auditory deprivation and cochlear implantation. And then I will continue with studies on audiovisual and interactions in normal hearing listeners. And finally, And finally, I will talk about audiovisual interactions in patients with a cochlear implant, and I will also give some insight into the clinical implications of these altered audiovisual interactions in these patients. So cochlear implant is an auditory prosthesis which can be implanted in individuals with severe to profound sensory neural hearing loss. And here on the left side, you can see the different components of such a cochlear implant. So it is an outer component and an inner component. Specifically, we have here the CI, the cochlear implant processor, equipped with a microphone, and this microphone receives the acoustic signals. The signals are then transformed into digitally coded signals, and they are then projected to this external coil, signal coil. And the signals are then projected transcutaneously to the implanted part of the implant, where the signals then result in the activation of different electrodes, which are inserted into the cochlea. So here you can see a cochlea with this electrode array with the different electrodes. So depending on the company, we have between 12 and 22 electrodes. So only a few number of electrodes which have to provide information about many thousands of frequencies in the acoustic domain. So electric hearing is quite different compared to acoustic hearing, and implant users have to get used to these new artificial signals. And many of them have difficulties, not only in music perception, specifically music perception, they have difficulties, but some patients also have difficulties in speech perception, specifically in difficult speech conditions, for instance, speech with background noise. So I would like to give you a short impression of a situation of a cochlear implant user. I will show some simulations of a CI situation, speech simulation and music simulation. Oh, I hope it will work with, okay. So please tell me if you hear something. So I will first play a speech sound. Could you hear something?
Yes.
Okay, perfect, thank you. So this was a simulation of a speech signal. Of course, this is only a simulation, and we will never know how it is really like to hear with a cochlear implant, but this is an approximation of a CI situation. I will play you the original sound now.
Today is a sunny day. I like to ride my bike.
Again, the simulation. Okay, then I will play you a music example. So I don't know if you recognized, maybe not. This is the original one. So as you may have heard, the rhythm is better perceived than the frequency information. So the CI transmits better the temporal cues than the spectral cues. And finally, I will play you another music example.
Sweet dreams are made of things to disagree, travel the world and the seven seas. Sweet dreams are made of these. Who am I to disagree? Travel the world and the seven seas.
So as you may have heard, music perception is even more difficult than speech perception with a CI. And there are several reasons for difficulties with music and also with speech perception with a CI. So first, there is the problem or the factor that the CI processor degrades the acoustic signal. Then we have only a limited number of electrodes available. And finally, and very importantly, we have the fact that the electrodes generate an electrical field which spreads out and which leads to an unspecific stimulation of auditory nerve fibers. So we have the simultaneous activation of many nerve fibers at the same time, and therefore we have a very poor frequency resolution by electrical stimulation. So that nevertheless, many CI patients learn to adapt to these artificial signals after implantation, and they improve in speech recognition ability over the first month of CI experience. Here below on the left side, you can see a learning curve of CI users Lennartz and colleagues, they examined these speech scores in a very huge sample size and for different age groups. And as you can see, this learning curve is similar across the different age groups. And you also can see that this learning curve approaches a stable level after several months of CI experience. So this learning curve would not be possible without the intrinsic capacity of the central auditory system to adapt to these new artificial signals. And this ability of the central nervous system to adapt to this changing environment is also called cortical plasticity. So how can we study cortical plasticity in cochlear implant users? Theoretically, there would be the option of MRI, because nowadays all of the CI companies that provide MR-compatible CI devices. Nevertheless, still with these MR-compatible devices, we have a problem of huge artifacts given by the CI, especially in the ipsilateral hemisphere. And nowadays, of course, this MRI technique is not applied to study cortical plasticity in CI users. Then we have PET imaging, of course, and there are several PET studies with CI users. However, this technique uses radioactive tracers, and this may be problematic in terms of longitudinal studies, and especially when we want to look at cortical changes in children. By contrast, as already Maika announced, EEG electroencephalography is a very promising technique. It's cost-effective and safe, so we can use this technique without limitations in longitudinal studies in children. And so this is a very promising technique in CI users. Nevertheless, also here we have the challenge of a CI artifact, which is provided by the CI. However, nowadays we have techniques to significantly reduce this artifact, specifically the independent component analysis, which allows us to study EEG signals in CI users. So EEG seems to be a suitable tool to study cortical changes in cochlear implant users. Specifically, there are several studies on CI users looking at ERPs, event-related potentials, which are defined as small changes in the electrical activity of neural populations in the cortex that are elicited by an external or internal event. So by means of these ERPs, we look at the synchronous activity of many thousands of neurons, of activated neurons, and we have specific analysis available. So for instance, we can look at ERP waveforms over the time for specific channel location, and we can compare these ERP waveforms between different conditions or group. But more promising is the use of more complex EEG measures like the voltage map, which includes the information of many EEG channels at the same time. And we also have the option of source analysis to estimate the neural generators of our ERP signals and to look at configurations of neural generators and look at differences between groups or conditions. So I would like to show you some results about cortical changes in CI users. I will start with an ERP study, which we conducted in Oldenburg. This is a prospective longitudinal study looking or testing CI users at different recording sessions, 4 different recording sessions, and we tested the participants, CI users as well as normal hearing listeners, with frequency modulated sounds. And we looked at the auditory cortex activation, ipsilateral and contralateral to the stimulated ear. And here you can see the results for the normal hearing listeners on the left side and for the CI users on the right side. So we can see, we can see here in red the activation of the contralateral auditory cortex to the stimulated ear, which is enhanced compared to the ipsilateral auditory cortex activation. And there is a stable response in the normal hearing listeners as expected. When we, however, look at the group of CI users, we see here dramatic changes over the first year of CI experience. So we see here a very tiny little response after 1 week of CI experience. However, one year later, we see a much larger and pronounced response in both the contralateral and ipsilateral auditory cortex. And when we look in more detail at, about the latency and amplitude of this response, we see that over the time, the latency of the cortical response decreases and the amplitude increases in both hemispheres. And at the same time, we also have an increase in speech recognition ability, indicating that these cortical changes allow the enhanced speech recognition ability with the CI. So these changes in the auditory cortex after implantation have also been reported by PET studies, for instance, by Giraud and colleagues. And they also showed that the CI users, they develop a speech-specific response pattern, indicating that the CI users develop a functional specialization in auditory cortex activation. So together we can say that these changes in auditory cortex activation in response to auditory stimuli can be observed in CI users, and these changes are also called intramodal plasticity. However, we could also show that the cortical changes in CI users are not limited, not restricted to auditory functions. Here I present you another study with visual stimuli. So in this study, we tested the CI users and normal hearing listeners just with very basic, simple checkerboard patterns with different luminance ratios. And we looked at the visual responses to these checkerboard patterns, and we found that the CI users recruit not only the visual cortex, but also the auditory cortex during this purely visual task. Here you can see the results for the CI users in red, and in black the normal hearing listeners. And you can see that in general the CI users show an enhanced response in the auditory cortex to this visual stimuli, especially on the right side, in the right hemisphere. And there is an increasing activation in this right auditory cortex with increasing luminance ratio. So we can say that the CI users show also a takeover of the auditory cortex by means of visual functions. So a visual takeover of auditory cortex, which can also be called cross-model plasticity. Interestingly, we found correlations between this visual activation in the auditory cortex and speech recognition ability and the duration of deafness. Specifically, individuals with a stronger visual activation of the auditory cortex had a poorer speech recognition ability, a poorer CI outcome, indicating that this visual response in the auditory cortex is maladaptive in terms of auditory rehabilitation. In addition, we found a positive correlation between this cross-model activation and the duration of deafness, indicating that a longer duration of deafness is related to an increased cross-model plasticity. So it seems that this cross-model reorganization is induced at the time of sensory deprivation before implantation, and it reverses at least partially after implantation. So here on the right side, you see the results of a study from Rouget and colleagues, a PET study, longitudinal study, where the CI users were tested at 2 different time points, shortly after CI switch on and 6 months after CI experience. And they showed that the CI users have a reduced visual activation of auditory cortex 6 months after CI experience, indicating a reversal of this reorganization in the auditory cortex. Cross-model plasticity was also observed in congenitally deaf individuals without the CI. For instance, by Finney and colleagues, who showed that these congenitally deaf individuals recruit the auditory cortex during purely visual information processing. The same group of participants also shows enhanced visual abilities. Here, for instance, the results of Hautal and colleagues, where here in this study we looked at the motion direction discrimination ability. We compared motion direction discrimination between deaf individuals and normal hearing listeners. And we found that specifically in difficult listening, difficult visual conditions, the deaf individuals were much faster compared to the normal hearing listeners, indicating that these deaf individuals have improved visual abilities. So taken together, these results suggests that functional reorganization of the auditory cortex allows better visual abilities. So this functional reorganization provides the neural substrate of these improved visual abilities, at least during the time of sensory deprivation. So we can say cross-model changes have been observed both in congenitally deaf individuals and in cochlear implant users. And this reorganization seems to be induced at the time of sensory deprivation. And it seems that this reorganization is adaptive in terms of enhanced visual abilities. However, it may be also maladaptive in terms of auditory rehabilitation after implantation, as this reorganization may prevent a full, complete adaptation to the auditory signal after implantation. However, the story may be not so simple, but because there is a result from Stropal and colleagues who showed that indeed CI users may also have enhanced visual abilities compared to the normal hearing listeners, and this enhanced visual ability is related to this cross-modal activation in the auditory cortex. So specifically, the CI users who showed a stronger reorganization in the auditory cortex, they also showed enhanced visual abilities in the lip reading task, indicating that at least in specific visual conditions, this reorganization of the auditory cortex may be beneficial. So I talked about the differences or alterations in CI users in terms of processing of unisensory auditory and unisensory visual stimuli. But now the question, what about multisensory processing? Do CI users show changes in these multisensory conditions? Multisensory conditions, of course, are very interesting because these conditions are more ecologically valid. So they are more everyday situations compared to unisensory conditions. However, before I go into detail about CI users, I would like to present you two studies about normal hearing listeners. Here I show you the results from Ross and colleagues, a behavioral study on normal hearing listeners, examining the visual influence on auditory speech perception in normal hearing listeners. Here, the normal hearing listeners were tested with words in a purely auditory condition or in an audiovisual condition. And these words were presented together with background noise at different signal-to-noise ratios. So, for instance, -24 dB signal-to-noise ratio is a very difficult listening situation because the speech signal is 24 dB softer compared to the background noise. However, when the signal-noise ratio gets less negative, approaches zero, then the auditory performance, of course, increases. And you can see here this performance increase, which is very clear in the auditory-only condition. And very interestingly, for the audiovisual condition, we can also see such an increase. And however, we can also see a general change in this line. So we can see a generally improved speech recognition ability in this audiovisual condition when compared to the auditory-only condition, indicating that the normal hearing listeners have a very strong influence due to the visual modality in difficult auditory listening situations. So what about other methods? Can we use, for instance, ERPs to study audiovisual interactions in normal hearing listeners as well? The answer is yes. We can also have a very good insight into audiovisual interactions when we use ERPs. For instance, Stecklenburg and colleagues used speech and non-speech stimuli, particularly syllables and natural actions, to look at the interactions. So they presented syllables and these natural actions like clapping hands or tapping a spoon on a cup. And they presented the stimuli in a purely visual, in a purely auditory, or in an audiovisual condition. In addition, there was also a control condition, just a fixation dot on the screen. The authors examined multisensory interactions by looking at difference waveforms. So they compared the ERPs computed by means of difference waveforms. So here on the right side of the equation, we have audiovisual minus visual. So they subtracted the visual ERP from the audiovisual ERP. And this difference waveform represents the visual modulation of the auditory response. On the left side of the equation, we have auditory ERP minus control, and this equation, or this curve, this difference waveform, represents the auditory response to the stimuli without the visual response to the fixation dot. So comparing these two difference waveforms indicates or provides some information about multisensory interactions, and indeed, here, the authors showed differences between these difference waveforms, showing that the AV minus V, representing the visually modulated auditory response, is reduced in amplitude and shorter in latency, both at the N1 and P2 latency, and both for the speech and non-speech condition, indicating that there is a multisensory interaction going on at these processing levels. So taken together, there is a visually induced speeding up and suppression of auditory ERPs in normal hearing listeners. And this multisensory interaction is not restricted to speech conditions, but can also be observed in non-speech conditions in these natural actions. So more interestingly, of course, is the question whether these multisensory interactions are also present in CI users, and perhaps whether these interactions are even enhanced because the CI users may develop compensatory strategies due to the limited CI input. So the question is, do CI users show enhanced visual impact on auditory speech perception? Here I show you the results from a behavioral study performed by Rogy and colleagues. Here, the participants were tested with a word recognition task, and the participants were tested in many different recording sessions, once before implantation and then several times after implantation. And you see here the results for the visual only, for the auditory only, and for the audiovisual condition. In blue, you can see the visual performance before implantation, which is quite high in the CI users and higher compared to the normal hearing listeners. And interestingly, this visual performance remains on this high level even after implantation, indicating that speech reading or visual lip reading is still very important also after implantation. For the auditory only and the audiovisual condition, here indicated as green and red bars, you can see that there is a strong increase in the performance, which indicates, of course, that the CI users highly benefit from the implant. So there is an increase in auditory and audiovisual speech comprehension. And interestingly, also we see that here on the right side that the CI users also show in general a high audiovisual gain, which is higher compared to the normal hearing listeners. So here on the right side, you can see the performance in the audiovisual condition as a function of the purely auditory condition. And the diagonal represents the performance which is identical between the two conditions. And every single dot represents a single subject. You can see here the blue dots represent the CI users, and the red and green dots represent the normal hearing listeners. And you can see here that the blue dots, they are in general quite here on the left side on the corner, sorry. And these blue dots, they in general show that the CI users have in general a stronger audiovisual gain compared to the normal hearing listeners. So they have a strong visual benefit. It seems that this visual benefit, which is stronger in CI users, however, depends on the proficiency in the CI users. So there may be, it seems that there is a difference between proficient and non-proficient CI users. So between CI users who have a good speech recognition ability and those who have a poorer speech recognition ability with the CI. So there are some studies using syllables, purely auditory, visual syllables, or audiovisual congruent syllables. And for instance, Tremblay and colleagues, they have shown that the non-proficient CI users who have a poor speech recognition ability in speech tasks, they also show a poor identification of syllables or poorer compared to the proficient CI users, as expected, of course. And the normal hearing listeners here, as indicated by this gray bar, they show, of course, a very high performance, around 100%. Now, interestingly, this Tremblay and colleagues study showed that there is also an interesting result on the incongruent conditions. So here, the authors used auditory stimuli, PA, which were combined with visual stimulus CA. And this combination of syllables may result in a fusion percept, in an illusion, which is also called McGurk effect. And I would like to illustrate or show you such a fusion percept. Maybe some of you may have this fusion percept. So I'll play the video.
Pa.
Again.
Pa.
So maybe some of you may have the impression that there's something weird with this syllable. So because, of course, the auditory and the visual information is different, and in some of you, there may be a fusion percept, a different percept than Pa and Ka, specifically the percept of Ta. So what about the CI users? Here you can see on the right side the results for this incongruent condition. So in case of the incongruent condition, the participants may report either the auditory part of the stimulus, the visual part of the stimulus, or this fusion percept. And here you can see that the normal hearing listeners and the proficient CI users, they were more likely to report the auditory part of the stimulus. And the CI users with a poor speech recognition ability, they were more likely to report the visual part of the stimulus. Regarding the fusion percept, you can see that all of the groups had some of these fusions. However, because of this huge variance in every group, there was no group difference. So in general, we can say that the poor CI users, they show a strong visual influence, a stronger visual influence compared to the proficient CI users. So taken together, CI patients with a poor CI outcome have a particularly strong visual influence in speech conditions. So what about the electrophysiological correlates of this visual influence on auditory processing? We performed a study with a very simple task, a detection paradigm, so a speeded response task with a very basic auditory and visual stimuli, pure tones and white discs presented on the screen. And the stimuli were presented either in an auditory only, in a visual only, or in an audiovisual condition. And the task was just that the participants had to press a button whenever they perceived one of the syllables, the stimulus. Good. We tested normal hearing listeners as well as implant users. Specifically, we tested CI users and a group of implant users with an auditory brainstem implant. So this implant users have an electrode array in the cochlear nucleus in the brainstem, because these patients do not have an auditory nerve which can be stimulated. So we compared the performance between these three different groups. And here on the right side, you can see the response times, response times for every condition: in visual in blue, auditory in red, and green audiovisual. For normal hearing listeners, CI users, and ABI users. And you can see in all groups a multisensory effect, the shortest response time for the audiovisual compared to the visual only and auditory only condition. So there is an audiovisual benefit in all groups. And on the ERP level, so on the processing level, we also found a specific group effect. Here we can see the activation in the auditory cortex for the normal hearing listeners, CI users, and ABI users. So we did a source analysis and looked at the auditory cortex. And here you see in black the response in the auditory cortex to purely auditory stimuli. And in red, you can see the response in the auditory cortex to the so-called visually modulated response. So again, as in this Stecklenburg study, we also did this difference wave, as we computed the difference wave AV minus V, and which, as I said, represents the visually modulated auditory response. And you can see here that in all groups, there is a difference between the auditory only and visually modulated response. However, the difference is enhanced for the two implanted groups, which you can see also on the right side. So we have, in general, a stronger visual modulation of the auditory response in the auditory cortex for the two implanted groups when compared to the normal hearing listeners. So this indicates an audiovisual coupling between the auditory and the visual system. And we interpret this result as indicating that the CI users have used this visual information to decode the limited CI signal. So this audiovisual coupling helps the CI users to improve the auditory performance. So this strong visual influence on auditory processing, we could also observe in more complex stimulus conditions. And here I show you the results of a study where we have this nice cooperation with Micah. And here in this task, or in this study, we used a continuous word recognition task where we presented naturalistic auditory and visual objects. Here you can see here some examples. So we presented these objects either in a purely auditory condition or in an audiovisual condition. And in the audiovisual condition, the objects could be either congruent or meaningless. So congruent means we have the sound of a car and the image of a car, and meaningless means that we have the sound of a car and the image of this very random dot pattern, so a very meaningless visual cue. And the task was here that the participants had to indicate whether the current object was presented for the first time or whether it was presented already at a previous time. Or in other words, they had to say whether it is an initial trial or whether it is a repetition trial. Here you can see the results. We can see here the behavioral results, the recognition ability, separately for the CI users and for the normal hearing listeners for the three different conditions: audiovisual meaningless with this random dot pattern, auditory only, and congruent audiovisual. And you can see here that both groups show the highest performance, the highest recognition ability when this object was previously presented with a congruent visual image. And in both groups, we see a similar pattern. So this after this congruent audiovisual condition was followed then by auditory only and by a meaningless audiovisual condition. So a similar pattern in the two groups. However, when we look at the differences in the performance between the different conditions separately for each group, we can see that there is a stronger difference, meaning a stronger audiovisual gain for the CI users when compared to the normal hearing listeners, specifically for conditions with congruent visual information. So interestingly, we also looked at the ERPs, and we also found on the ERP level group differences. So when you look carefully here at the topographies across the time, so between 100 and 350 milliseconds after stimulus onset, separately for the two different groups and for the two audiovisual conditions, you can see that these topographies, they change across time. And in particular, the CI users show here a large positivity here, this red area over frontal regions. This large positivity is more pronounced and is extended when compared to the normal hearing listeners and also when compared to the meaningless audiovisual condition. And we did sophisticated topographical analysis by means of this Cortical software, and where we found that this positivity here, also as referred as congruency-related response, that this positivity is more present in the congruent audiovisual condition compared to the meaningless audiovisual condition. So here you can again see here this congruency-related response map, which is more present here for the congruent compared to the meaningless condition. And you also can see that, we can also see that the normal hearing listeners, they do not differentiate between the two conditions in this map. Interestingly, we also found that this congruency-related response is positively related to the auditory recognition ability in the CI users. So the more present this map in the congruent condition, the better also the auditory recognition ability of the objects, and indicating that there is a strong connection between this altered audiovisual processing in the congruent condition and the behavioral performance, the benefit in the auditory recognition ability. So to summarize, we have in the CI users this effect specifically for the congruent conditions, showing a strong audiovisual gain and an altered audiovisual cortical processing. These results may also be of therapeutic relevance because they indicate that the CI users may highly benefit from an audiovisual training, and which may fasten and enhance the auditory rehabilitation after implantation. Okay, previous PET studies have also shown that the CI users have altered processing in the auditory and visual cortex over the first month after implantation. Here I shortly show you the results from Giraud and colleagues. The authors here showed that the CI users show an increased activation in the auditory cortex to auditory stimuli over the first years after implantation, and at the same time the CI users show also an increased activation in the visual cortex to this purely auditory stimuli. So there is a similar increase in activation, not only in auditory, but also in visual cortices. And we also, there is also the result that from Strelikov and colleagues, that the CI users specifically after several months of CI experience show a strong coupling, a strong correlation between activation in the visual cortex and the auditory cortex during an audiovisual task. So this indicates that that experienced CI users show a strong coupling between activation in the visual and auditory cortex. So there is a strong audiovisual coupling, and this may limit, or this may allow these individuals to compensate for the limited auditory input to improve to the auditory performance. It seems that this audiovisual coupling is particularly important during the first time after implantation, because at this time the CI users have to match these highly artificial signals with the visual cues, and this coupling may help these individuals to match the auditory and visual parts of the signal. So finally, I would go to the question whether we can use visual ERPs in the clinical context, because there is the hope that we can use objective measures in order to improve the prediction of the CI outcome after implantation. So here I just show you the preliminary results of a prospective longitudinal study. Here we examined visual ERPs from CI users before implantation, and we correlated these visual ERPs with the CI performance 6 months after implantation. The CI users or CI candidates at this time, they were tested with visual stimuli. They had to perform a lip reading task in an attended and in an unattended condition. And here you see the preliminary results here for the normal hearing listeners and for the CI candidates. You see the visual responses for occipital channels. And you see that there is a difference in the visual response at this measurement time point, both for the P1 and P2 response. And very interestingly, we see here that this P1 amplitude correlates positively with the CI outcome. So in other words, the stronger the visual response before implantation, the better the CI outcome after implantation. However, these are preliminary results, and we will, of course, record more data and check whether this correlation is then still observable. So to summarize my talk, I presented several studies on audiovisual interactions in CI users. On the behavioral level, I showed studies which revealed a strong audiovisual gain in the CI users, and this gain seems to be particularly pronounced when the CI users have a poor speech recognition ability. Okay. So, so we have a strong visual impact on auditory speech perception in CI users, and this visual impact seems to be stronger in non-proficient CI users. On the cortical level, we also found interesting results. Here, the CI users showed activation in the auditory cortex, not only to auditory stimuli, but also to visual stimuli, indicating a visual takeover of auditory functions in CI users. And it seems that this visual takeover is maladaptive in terms of auditory rehabilitation after implantation. Regarding visual ERPs, we found in our preliminary results a positive correlation between the P1 response and the CI outcome, indicating that these visual responses recorded before implantation may help indicate or may help to predict the CI outcome. Further, I showed you results about the visual modulation of ERPs, of auditory ERPs in CI users, both for simple stimuli as well as for audiovisual stimuli. And these ERP results indicate that there is a strong coupling between the auditory and visual cortex, which may allow the CI users to compensate for the limited CI input. Okay, so so I'm at the end of my talk, and I'm happy to discuss with you about some results.
Thank you very, very much, Pascale, for this wonderful talk about some of your work on the importance of understanding plasticity and auditory cortices of implanted individuals. I'm sure there's lots and lots of questions out there. I have a long list, but I have privileged access to you, so I'd rather defer to people who don't. You can either raise your Krissa, I see you have your hand up first.
Hi, Pascale. First of all, the talk was amazing.
Thank you.
Thanks for it. I'm sorry, I'm walking to the lab because so there is a lot of noise because I have another meeting. But I wanted to ask you about, I guess most of the people in the studies that you presented, they got cochlear implants as adults, right?
Yes.
So how would it be? Would there be a better adaptation if they were getting cochlear implants as children are the studies to show that, and also how it would interact with cross-modal adaptation if they were getting them as kids? So long-term users of cochlear implants, and actually in an age that the brain adapts more, right?
So if I got you correctly, you ask about children, cross-model reorganization in children.
Yeah, and long-term users of cochlear implants. Yeah, but when they got them as children, yeah.
Okay, so first of all, the results which I showed you in the talk, of course, they were on adults, post-lingually deafened adults, but also experienced adults. So all of these CI users had at least 12 months of CI experience. And we know from many data that the CI users approach a stable level around 3 to 6 months after implantation. So we can assume that there would not be many other changes after 1 year of CI experience. And regarding the children, of course, there are also some studies, for instance, from Anu Sharma, and they also show CrossModel reorganization in children as well. And it seems, or there is first indication that this reorganization is more pronounced in prelingually deaf individuals. So when there is no acoustic input during language acquisition. So it seems that these critical time windows are necessary to have a good adaptation to the implant signal, and that the cross-model reorganization is stronger in when there is an early onset of the deprivation. And regarding audiovisual interactions, there are also studies, for instance, from Shore and colleagues. They also examined this McGurk effect in children. And very interestingly, they showed that the children, they also showed a visual dominance. So they reported more the visual part of the syllable compared to the auditory part, whereas the normal hearing listeners, the normal hearing children, they reported more the auditory syllable than the visual syllable. And there were only few CI children who had this fusion percept. But interestingly, these children who had this fusion percept, they were all of them were implanted at early age, so before 2.5 years. So this indicates that early auditory experience with the CI is necessary to have this fusion percept.
Okay, cool. Yeah, that's what I would expect as well. But I was curious to see. Thanks very much.
You're welcome.
Thank you.
Wonderful. Other questions, remarks? So, yes, Olivia.
I have a question here. Hello. Good morning. Thank you very much for this presentation. It was really interesting, as I'm not an expert in the domain of audiovisual stimuli and perception. I have a question regarding the PET acquisition. What was the radio tracer used? Was it like oxygen, 15 water, or something like that?
Oh, this is because I was not involved in this Giro studies. I have to say I would have to read that in the paper. but I think it's glucose metabolism, but I'm not, perhaps
Okay.
somebody, Michael, do you know?
I believe it was fluorodeoxyglucose, if I remember right. But
Yeah.
Okay.
in the end, I wasn't involved in that study either. But Annelies is a reachable and regional partner, so I'm sure we can ask her directly, and I'm sure it's in the paper as well.
Yeah, because I heard recently about some traces to this kind of signal perception for patients having cochlear implants, and that wasn't FDG or fluor with glucose. So this is why I asked this question. But thank you very much anyway.
Are there other questions before I pose a few of my own? So one of the questions that I've been confronting, and I'd be very eager to have your input on, is the importance of bilateral implantation. More often than not, at least X years ago, the standard of care was unilateral implantation, and more there's recognition that bilateral implantation is actually quite advantageous. I was wondering what your thoughts were on that, and what the implications are in terms of some of the mechanisms that you've been highlighting in your talk today.
Yes, a very good question, and actual question, of course. So we can say from clinic point of view that we always look at each ear separately. So when the hearing loss is worse or is so bad, then we implant irrespective or regardless whether the other ear is implanted or it's normal hearing. So every ear is looked at separately. So this is from clinical perspective. And in general, I can say from my experience that many patients, they highly benefit from the second implant when they also have hearing loss on the other ear. Because, for instance, the hearing aid has a strong delay compared to the CI. So it's several milliseconds difference between the hearing aid and the CI. And then sometimes they hear worse with the additional hearing aid, so they have to remove the hearing aid. So it's better to use a second CI in terms of timing, so they improve not only in speech recognition ability, but also in spatial localization, because they have this temporal information. And regarding the reorganization, I have to admit I'm not aware of a study which looked at different subgroups of CI patients, unisensory hearing loss, unilateral hearing loss, bilateral hearing loss, which is of course a very important issue to look at. What is the contribution of the second ear? And we currently have first recordings on that because we want to look at different subgroups, because the CI group is very heterogeneous and we should more more control for the different variables. Yes, I totally agree that this is a very important issue.
Great. Thank you. Are there other questions or remarks? I don't see any. So with that, I think I'll thank you personally again for this delightful overview of your work. We're very privileged to have our collaboration with you, and look forward to continuing that for many, many years to come.
Thank you very much too.
I'll hand things over again to Pina.
Okay, thank you both for a great talk and for the introduction. It's always nice to see how the collaborations are, happen, and what is like the activity that is going on between the section heads and the sections and the different partners. As you are all part of the CIBM community, it's nice to see you and to meet you.